My name is Stephen Krapp. I work for MaxLinear. I've been around the cable industry now for 20 years. It seems like a blink of an eye. But I started in '99 back on the DOCSIS 1.1 spec when DOCSIS 1.1 was going to change the world. I've worked on DOCSIS 2.0, 3.0, and now here we are on the cusp of 4.0, but we're going to take a step back today and look at it in depth a little bit at DOCSIS 3.1 and see how we can get the most out of our DOCSIS 3.1 deployments. We have two great presenters. We have, I'll introduce the presenters individually as they come up, but two great papers, and so I encourage you to read the papers, but while you're here, enjoy the presentation. First up, we have Matthew Alford. Matthew works for Shaw Cable. He's worked there since 1998, if I got that right.
I did.
And Matthew has done a number of jobs while he's worked at Shaw. He's done anything from customer support to operational support. We support the operation guys, and then network deployment. However, these days, Matthew focuses most of his time on designing and deploying DOCSIS networks on the access side. So, Matthew.
Thank you. Okay.
Might need to move that microphone up.
Yeah, I probably do. I'm a little tall. Yeah, it worked. Oh, that's always good. Okay. So I'm going to talk about transition to a 3.1 network, and not just transitioning to turning on Ofdm or Ofdm-A, but how do we transition also to just 3.1? Because I think that also needs to be discussed. So it's how we optimize today, how we move forward, maybe even the best way to deploy it today if you haven't done it already. But let's also talk about a little bit of future and how can we get rid of that legacy stuff and what's going to assist us to do that. Just a little bit. So Ofdm, last summer Shaw deployed Ofdm across our network. We were pretty aggressive on our design. We did multiple profiles. We did all this fancy stuff. And then we started having massive problems everywhere. Techs aren't familiar with the technology. They're just getting used to the new meters. So we quickly revamped our design and went very simple. So we stayed to the 256 QAM single profile design. Obviously, techs are very familiar with single carrier QAM at 256, so why try to shoot for the moon? Let's just make this simple. So you lose that spacing gain, so you still gain capacity per megahertz here, but it's just a simple design. You're not worried about profile switching. If the modems use the Ofdm channel, they can hopefully pass data at 256 QAM. It's going to be a pretty reliable channel on all those things considered. We also had to reanalyze our PLC. We had some PLC errors in some areas of our plant. And so we intentionally reevaluated it. We looked at the new upcoming wireless spectrum options at 600 and 700 megahertz and made sure our PLC was kind of avoiding off-air interference as much as possible and make sure that signal was clean. And then we also had some problems where a customer would swap their 3.1 modem from a 3.0 modem and their service would be crappy because the Ofdm channel wasn't working. And they would happen to use that 3.1 channel to register. So what we experienced with that was if we just made a non-primary channel, that modem would shed that Ofdm channel at will without impacting their service. So then it was a big, because we deployed Ofdm up near 750 and down to about 650. And so we had some roll-off issues in some areas of the plant, and that way modems can shed that channel if they're not happy with it, and they can still use 31 carriers of single carrier QAM. And to the customer, they're blind to the problem, which is great. So that's why we chose to do that. And I really recommend this if you haven't deployed Ofdm, it's a very simple way to do it without massive change. So let's talk about things you want to do to get to a more complex Ofdm setup and to get even more capacity out of it. Because in the long run, we want to maximize that capacity. So PNM is a great way to do that. And the data you want out of PNM is that RxMER. And Ron's going to be talking about that in great detail. And we really want that so we can start to do an analysis on the Ofdm carrier or our Ofdm-A carriers. And so you know what kind of signal quality you have in that area of the plant, and you know what kind of capacity you can run on a maybe per modem group area, and we'll talk about PMA in a bit here. But it's really, you actually know the quality of your plant without sending text to the field with meters. And that's really the beauty of PNM. And also, if this data is available to frontline staff, it really saves them potentially sending the wrong tech to the house. They can know maybe it's an outside plant problem, because groups of modems have the problem. And that's, send the right tech to the right problem is a good idea. So PMA. So PMA is a very powerful analytics application that takes the RxMER data and does it, and basically builds profiles for groups and modems. And so at Shaw here, we're looking at how many profiles do we need? And we've done some analysis, and we were thinking 7 or 8 downstream profiles should be enough to handle most plant conditions. If you're dealing with like N+4, N+5 scenario, you want that many profiles, because every time you're going through an active, you're gonna have different plant conditions. And you can kind of create enough clusters of profiles for every type of performance in modem and maximize that capacity. But you're not just maximizing capacity, you're also going to maximize the reliability for that service for those modems. So that's very important. And so our plan is to maintain that single profile A is 256 QAM, just a flat profile. And then we're going to use variable bit loading to maximize capacity. So our profile can do mostly 4K QAM, except for you have roll off for the last 20 megahertz when you need to downgrade it to 2K QAM. That's what we'll set that downstream profile up to do. So we're going to use these additional 7 profiles to kind of build custom profile groups for each server group. Now you obviously realize this would be per server group configuration. They're all going to be different, or you know, there'll be differences all over the network. So the automations will be our key piece for this. And so during testing, because we're running 256 QAM, we started seeing a lot of nodes be able to perform at 4K QAM for the majority, but not entirely, and without, you know, and being happy at that profile. With some adjustments, we're getting about 40% gains from 256 QAM, which is lovely to see, you know, without asking for more frequencies from your, you know, video department, because you're trying to, hey, less single carrier QAMs, guys. That's always a challenge. So if you can upgrade your modulation profiles, you can get more capacity. And so we're typically using 3 to 4 current zones of variable loading, just so everyone's aware. More zones obviously would give you a little more granularity of your change. So if you look at Ofdm after this analytics and you put it into your network, you're going to have 8 downstream profiles. And 7 of them we're probably using variable bit loading. And yeah, but if you're going to do it full scale, I highly suggest you're going to be fully automated and you're going to fully implement that change into the network. So you're going to automatically go in and change that config every time potentially you do analysis on the plant. And so that's, you know, it's going to be a lot of work, but I think if we built our automated systems for that, it's going to be a huge benefit to your capacity. Now, I know we're not here to talk about mid-split in entirety, but I think this has a big deal to do, I think, with OFDMA. So with mid-split, you're going to add a lot of capacity. I say 150% because I'm assuming 5 to 12 megahertz, you're probably, or maybe in 13 megahertz, you're not going to be able to use, maybe, especially at single carrier QAM. It's fairly noisy out there. So there's a huge gain about going to mid-split. So Shaw's actively moving to a lot of mid-split, and part of that mid-split plan is to eventually use OFDMA there. And so we can use it in our new carriers. Most of you don't have old 2.0 modems with 85 meg return. You're going to have 3.0 modems, 3.1 modems with 85 meg return. And maybe, it depends when you got into that game, it might be majority 3.1 modems. So it's a great place to use OFDMA. We did identify some risks with mid-split. We've had modems problems with registering. Especially with a drop 5 to 42 meg drop amps are a big problem. So if you have an 85 meg return modem in a 5 to 42 meg drop amp, the CM test is telling them there's frequencies above. They can have a lot of problems registering. We've seen up to an hour delay on registration. So you be very aware of that problem. We've had to address that. We've reduced upstream primary channels to mitigate that problem, if you're curious. If you want to know more, ask me later. Another key piece of any type of major technology change, so 3.0 to 3.1 is the primary example of this. This is our mid-split distribution. There's a huge correlation, obviously, to the amount of modems you have in your network that are capable of the new technology and your new technology being used. And it's very inefficient to lower the distribution is. So if you only have 20% 85 meg return modems in this example, you know, you're going to use less than 20% of that new frequencies. So it's very important to get ahead of the game there. if you just want to use the traditional way of deploying. So FDMA, you need 10 megahertz, which is a great challenge if you're in a 5 to 42 megahertz plant world. This is why I think most operators are probably going to wait till they have mid-split or higher to deploy this. So you don't have to sacrifice a single carrier QAM. And yeah, I'm trying to remember what I was saying. Oh, yeah. Yeah, anyway, so you can deploy a very similar design to OFDMA that you did for FDM. So you could deploy IUC set to 64 QAM. You're used to 64 QAM and upstream here. You could run the PMA process against the OFDMA channel as well, and then start building the profiles. It's a very similar process. Or you can just build flat profiles like this. It depends where you're deploying it. If you're going into the noise area of the plant, you probably want to use PMA for sure. If you're going into above 42 megahertz, it's generally a lot more cleaner up there. You probably could get away with a lot more flat profiling and you know, hold off in the PMA process if you want to. Oh, lots of time. Actually, the last thing I want to talk about, I'm really whipping through this. Max schedulers are actually becoming a big problem. I noticed this during our OFDM deployment. We had an area that had significant utilization of single carrier QAM, you know, well above our design capacity. You know, we're seeing channels use up to 38 megabits per second on a downstream channel. So I would say it's congested and can't get worse. So we launched OFDM there. It was a slow process to get OFDM modems out there. We had about 20 out of the 800 modems on that node. It's a very remote node. And we noticed that the device, the moment that single carrier QAM had any capacity, it would start having the 3M modems go over there to single carrier QAM, and it's like the last place we want it to go. So I'm suggesting that I've talked to my vendor, but might want to talk to your vendor as well. Anytime there's a major technology change, we need max schedulers to be able to be more intelligent, to really force modems to the new technology. And yeah, so that's basically what my point of this slide is. We've seen the same thing with the K-modem distribution. You can wait for that, but if we can have a max scheduler that's intelligent about modems, and if they have 3.1 capacity, that it forces them to 3.1 instead of trying to use the old technology. And the benefit of doing that is, one, you'll have more reliable service from the new modems, which is good. And it will encourage, hopefully, customers will like your new modem better because it performs better. But two, you also know how much of the old you need. And this is, like, I think, how we transition to a 3.1 network. If you can start going at, you know what, I actually don't need 32 single carrier QAMs anymore. I only need 24 now because 3.1 modems are still, they need more OFDM. So if I can turn down more single carrier QAM, I can turn on more OFDM. And that gets you more efficiency per megahertz, which is all we look for in this industry. And that's all I have to talk about.
So I think we're going to stay up here and answer questions first, just because we're really good on time. So, is there any questions from the audience? All right, I have a question.
Okay.
So I was listening to your presentation, Matt. It was very informative. Did you guys? Now you're in Canada.
Yep.
And so the frequency bands may be different, but was there any issues with LTE ingress in the OFDM band that you deployed?
We did see it, so that definitely happened. Any off-air carrier can be a problem. We had a problem with HD cable channel in Edmonton, for example, was a problem. So yeah, we've had to move PLC carriers to avoid off-air problems. Yeah.
Yeah, and then is that something that the PMA application helped with as well, or would it do the bit loading around those carriers? Or
actually, we were using just K-modem status messaging to do that. We saw channels were shedding it because of PLC errors, so we sent text to that area and did off-air analysis and found the problem.
Or I guess the other option would be to choose a different location for the PLC, or is that
Yeah,
difficult to manage?
It depends how big your OFDM channel is. You can always move it around, right? So. Even if you didn't send someone out there, it's a simple thing of changing the PLC carrier where it is, and you can see if it performs differently. If you don't want to send a tech out analysis, the RxMER would have shown that problem. I'm sure, Ranek. You'll probably cover that. Yeah, so it's really about it's very flexible. That's the beauty of OFDM. It's very flexible. That's also, it's difficult because it can change so much.
All right.
Good information in there.
Thank you, Matt. That was very informative. I think it's very timely with 3.1 deployments starting to become more the de facto standard, and we're seeing lots of benefits. Up next, I have the pleasure of introducing Ranek. Ron is a 46-plus year veteran of the cable industry.
47 years, day after tomorrow.
I was just going to ask if this bio was old. And, so Ron was probably around for the early Ofdm deployments then? No. Early two-way deployments possibly. But
One way, early one way.
early one-way deployments. So, excellent. Ron is a fellow member of SCTE. He was inducted into the SCTE's Hall of Fame in 2010. He's co-recipient of the Chairman's Award, an SCTE Member of the Year, and member of the Cable TV Pioneers class in 1997. He received the Society's Excellence in Standards Award at Cable Tech Expo in 2016, and was recipient of the European Society for Broadband Professionals in 2016 as well. Numerous awards, numerous articles written. I know that I've learned a lot by reading a lot of Ron's articles over the years. I hope you've all been able to learn a lot from Ron's articles. We're going to learn a lot from Ron today. Ron, take it away.
I'm not quite as tall as Matt, so let me move this back to something that's more normal height-wise. Well, good afternoon, and thank you for coming to Cable Tech Expo this year, and thank you for coming to this session. Quick question, how many of you have deployed DOCSIS 3.1 in your networks? So no issues? Great, we can go. Excellent. No, just kidding on that part. The subject that Matt touched on did talk a little bit about the use of RxMER, receive modulation error ratio per subcarrier, as a metric for use in their PMA application, and that's a pretty valuable use for it. But there are other uses for MER, and I think those of you who have worked in the industry any length of time, particularly dealing with what we call digital signals in our networks, have found that modulation error ratio is a very, very valuable metric, and one that helps us to troubleshoot problems, at least to some extent. In many cases, MER is tied to node health scores and so on. Modulation error ratio there, though, as a standalone metric on what we call single carrier quadrature amplitude modulation, or SC-QAM signals, is a good metric, but it doesn't necessarily tell us why it's the value that it is. But if we take a step back for just a moment, what the heck is MER? And as you look at the slide, you can see there is a definition, and it applies to a single carrier QAM signal, an individual one, or an individual subcarrier within an OFDM signal. An OFDM signal comprises up to several thousand subcarriers. Well, each of those subcarriers is a QAM signal. That's it. Each one is a QAM signal. And of course, much like the case with our single carrier QAM channels in the network, we're interested in MER per something. Well, in the case of OFDM, it's the MER per subcarrier. But what is it? Well, more specifically, it's the ratio of average signal constellation power to average error constellation power. We call that digital complex baseband signal to noise ratio. So as you take a look at the diagram on the lower left part of the slide, you can see what we have would be the equivalent of a constellation display for one symbol, perhaps in an upper right quadrant of a QPSK signal. And here, the long arrow is a vector that represents the average symbol power for the RF at that point in time. And the way to visualize that is that, yes, we talk about digital signals on our networks, but let me ask the question, how many of you carry digital signals on your networks? That's a trick question because some of you have heard this before. And David, I think you've heard this before too. You don't. You carry analog signals on your network. Those digital signals are really analog signals. When we transmit digital data through our network, we're actually varying the amplitude and phase of an RF signal to represent digital data. And if you think of the angle of this vector as representing the instantaneous phase of the RF signal, and its length as representing the instantaneous power of that RF signal, at that point in time, that represents a symbol, which represents some group of bits. Well, the same thing applies whether it's a subcarrier on an Ofdm signal or a single carrier QAM signal. Where things start to get interesting is in the real world, the absolute or the instantaneous value of amplitude and phase is supposed to be an ideal value, but it's not. It's corrupted by noise and distortions and other things. So if we were to plot the length of this arrow and where the tip of that arrow appears over a period of time and draw a little dot where that is, we're going to get this little cloud here of dots that represent the instantaneous amplitude and phase of that signal. And the ratio of the average symbol power in this case to the average error power here is MER. That's what it is. Now push the page down button. There's the mathematical version of that. That's what's going on inside a QAM receiver in a cable modem, or in the case of an upstream line card on a CMTS. It's going through this particular little bit of math here, but in this case, this represents all of the symbols in the constellation. So we've got in the numerator the ideal positions, and then down here we have the error vectors. And you take the ratio of that, take the logarithm of that, multiply by 10, and you get MER and dB. And that's what it's all about. So another way to think of it is MER is basically how fuzzy the constellation display is, or how spread out it is. So you take a look at the two constellation displays on the lower part of this slide. You can see on the left side of it there, we've got pretty good MER because the symbol points are fairly close together, and that one shows about 27 dB or so MER. And on the right side, you can see that they're spread out, probably because of low carrier to noise ratio. And in that case, we've got about 17 dB MER. Now, there's an important point in this. I mentioned that the classic definition of MER is this ratio of average symbol power to average error power. Well, there's another way you can do that, at least in the numerator. You don't have to use the average symbol power. You can replace it with a constant if the constellation power is known, which is the case with DOCSIS 3.1 Ofdm RxMER. So we can use a constant, and it happens to be normalized to the number 1. So I'll show you that here in just a minute. Now, you've heard me use RxMER and MER. What's the difference? Well, MER is modulation error ratio. RxMER is receive modulation error ratio. Receive modulation error ratio, receive MER, is the MER measured in a digital receiver, so that could be the demodulator circuitry or receiver circuitry in a cable modem or digital set-top, or the upstream line card circuitry. So it's after demodulation of an individual single carrier QAM signal or an Ofdm subcarrier after adaptive equalization. Now, I mentioned a moment ago that an Ofdm signal comprises upwards of several thousand subcarriers, and keeping in mind that each one of those data subcarriers is a QAM signal. How on earth are you going to manage MER per subcarrier or RxMER per subcarrier if you've got thousands of those things? Well, you can do this. You can command the modem to return the values for RxMER for all the subcarriers. And this is from a real cable modem. However, there are several thousand values here, and that becomes a little bit cumbersome to try to manage, so I don't think we want to go down that path. So instead, we can plot the RxMER per subcarrier on a handy little graph, and most of the test equipment lets us do that. Now, before we get to that point, I do want to mention some details about the derivation of RxMER per subcarrier in Ofdm. And one of the bits of confusion that exists out there is that in Ofdm and in the world of downstream DOCSIS 3.1, the RxMER per subcarrier is measured using the pilots. the pilots, which are used to synchronize the cable modem to the CMTS and also for characterizing the channel, are boosted by 6 dB. So some people think, well, if I get an MER measurement from a subcarrier, in this case that's functioning as a pilot, that's boosted by 6 dB relative to the data subcarriers, then I need to do a conversion or compensate for this 6 dB difference in amplitude. And the answer is, no, you don't. And the reason is, if we go back to that formula that I mentioned before, we replace the symbol power with a known constant, in this case, for the data constellation power. And that's a known value. And one of the neat things about Ofdm and DOCSIS 3.1 is by using boosted subcarriers or boosted pilots to do the RxMER computation, the SNR can be really low, which normally would render demodulation unreliable. Well, because the pilot is boosted, the receiver is still able to demodulate that, and because it knows the value of that subcarrier, it knows what it is, so it can be really, really crummy SNR, and it can still determine a correct value for the RxMER. Now, as you look at this then, so if we're using this in the numerator, then the only thing that goes in the denominator is the error vector, the little red arrow here. And that gives us the ratio we want. We take the logarithm of it, multiply by 10, and now we have the RxMER per subcarrier. No correction for that amplitude difference is necessary. All right, so what does all this mean then? We take that list of thousands of subcarriers, and we can either read through it manually. Subcarrier number 1 is 42.1 dB. Subcarrier number 2 is, now that's not going to work. So what we can do is take advantage of the fact that the test equipment that is available to us today can plot the MER per subcarrier on a graph. And as you take a look at the graph that's on the screen here, you can see that in the vertical axis we have RxMER, and in the horizontal axis, depending on the instrument, can be frequency or subcarrier number. But what this shows is a plot of the RxMER value. So instead of having to go through that list manually and read it, the instrument has plotted it. The MER per subcarrier for subcarrier number 1 is 41 dB. For subcarrier number 2 is 40.2, and so on, all the way across the width of the Ofdm signal. By the way, this is a plot of RxMER per subcarrier off the Ofdm signal present in my subscriber drop in Denver. This is after node +3, and I'm connected to a 4 dB 2-port end-of-line tap. And you can see the average MER per subcarrier is about 41 dB, which is actually pretty good. All right, here's an example of an unimpaired RxMER per subcarrier. That looks pretty good. You look at that, it's a nice straight line, more or less. We've got the values up there hovering around 41 dB. This would easily support 4K QAM or 4096 QAM. Here's an example of RxMER per subcarrier with simulated ingress. And I created this to show that, okay, first of all, the impact of ingress in an Ofdm signal is not going to produce this nice, neat little drop in MER per subcarrier like you see here. I just wanted to illustrate that when a portion of the Ofdm signal is impaired, the MER on those subcarriers will drop. So they'll drop below the value of the rest of them. So in this case, we have a simulated example of an LTE signal that's 10 megahertz wide, causing the MER per subcarrier to drop about 10 dB in that part of the Ofdm signal. Now, I want to mention before I move on, there's another neat trick that can be done that I don't think any of the test equipment manufacturers are doing yet, and that is one can invert the plot of MER per subcarrier to get the negative RxMER per subcarrier, and what this gives you is a plot of the equalized noise floor, and you can see ingress sticking up above the noise floor. So just a hint to test equipment manufacturers. This is what real ingress looks like on an Ofdm signal. Here you can see some ingress at about 890 megahertz, and you can see that it's not that nice little even drop down in RxMER with the flat bottom on it, but instead it's a little jagged looking, but that's ingress at about 890 megahertz. Now here's an interesting thing that shows up from time to time, and that was one of the bits of inspiration for the work that we did to write this paper, because if you look at the paper, you'll see that it's got several co-authors on it. We did a lot of lab testing at Cable Labs, at ECLISA, and in some real cable systems. But it's what we call an edge roll-off. And as you take a look at the example in the upper left, you see there's no edge roll-off of the MER there, but here you can see the edge roll-off right there. And what causes that is the presence of an adjacent single carrier QAM channel next to the OFDM signal. Now in this case, some of the configuration values for the OFDM signal, specifically the cyclic prefix and roll-off period, have not been optimized to have for the presence of an adjacent signal. And the adjacent QAM signal is interfering with the first few subcarriers of the OFDM signal and causing their MER to drop. And that shows up as this roll-off at the edge of the OFDM signal. Now here's an example that's got a little bit of everything in it. This is real world. As you look at this, you can see edge roll-off, you can see examples of ingress, you can see kind of a general roll-off of the RX-MER per subcarrier going this way, suggesting some frequency response problem or degraded carrier-to-noise ratio at the upper end of the spectrum. There's also an exclusion band in here that the operator had plugged in there. So this has an exclusion band, an ingress, edge roll-off, and a lot of other things. So that's really a pretty nasty looking thing. What do you think of this? This was one that got our attention. Now, we're used to seeing on a spectrum analyzer display when a microreflection exists in the network, the resulting reflection causes standing waves or amplitude ripple on, say, a sweep or a spectrum analyzer display. For example, full band capture, you can see ripple or standing waves in the display. But this is not a frequency domain, or this is not a display of a spectrum analyzer shot. This is a display of RX-MER per subcarrier. And you'll notice that there is amplitude ripple in there. And initially, when some of this was first being seen by some folks, they said, well, it's kind of a strange looking oscillation that's going on. And we said, no, I think that's probably related to a microreflection. But what makes it weird is it doesn't always show up, even when there's a microreflection present all the time. This does not always show up in the RX-MER per subcarrier plot, and there's a reason for that. So to figure out what the heck was going on, I think we have a pretty good grasp as an industry that if the carrier-to-noise ratio drops, the RX-MER per subcarrier is going to drop. If you have a suck out in the frequency response, that's going to cause a suck out to, that is, cause a drop in the MER per subcarrier where the suck out is, and so on. But this was kind of an oddball one. So we set up this configuration at Cable Labs, and there are 5 main test configurations, and for each test configuration, there are 3 input levels to the test equipment and the cable modems, minus 10 dBmV, 0 dBmV, and plus 10 dBmV. And then as you look at the test configurations for all these scenarios, we had the reference setup where we just varied the input signal to the test setup. Then we created a microreflection and did the same thing, 3 input levels with the microreflection. Then we injected broadband noise before the microreflection. Then we did another set of tests injecting broadband noise after the microreflection. And then we did one final set of tests injecting broadband noise before and after the microreflection. And in all these cases, we set the AWGN source, that is the noise source, to produce a carrier-to-noise ratio of 35 dB. And we got some rather interesting results. The data that we captured is all detailed in the paper. The paper itself is 50-some pages long, has 90 figures. Now, understand that the 90 figures is most of all this data. So there's spectrum analyzer screenshot, cable modem channel estimate, we've got the RX-MER per subcarrier, and OFDM channel power. So there's a lot of good, very, very good information. Here are some examples of what it is that we saw in our testing. Now, in the upper left screenshot here, this is pretty typical of what we saw with test case 3B and 4B. So this is with the signal going through the microreflection, and the 3B and 4B, the B part means that the signal level is 0 dBmV at the input to the modems and the test equipment. And the 3 and the 4, if we go back, would be this case here and this case here. So one of them is with the noise injected before the microreflection, the other's with the noise injected after the microreflection. And this upper left screenshot is a spectrum analyzer display. So that's what you might see on a full band capture modem display of the OFDM signal or a conventional spectrum analyzer. So no surprises there. Signal's going through a microreflection, and we see the ripple in the frequency domain display on the spectrum analyzer. So, okay, that's expected. Now look at the upper right screenshot. This is RX-MER per subcarrier. That's for test case 3B. That's with the broadband noise injected before the microreflection. Now you'll notice that the RX-MER per subcarrier plot is essentially flat. It doesn't show the amplitude ripple, or if there's any there, it's extremely small. So you don't see that. You don't see it in that display. The lower left display is what's typical for test case 4B, so 0 dBmV input to the modems in the test setup. But here, the broadband noise is injected after the microreflection. And here, you do see the ripple in the MER per subcarrier plot. So here you don't see it, here you do see it. They're both going through the same microreflection. It's a function of where the broadband noise is injected. And I'm going to come back and explain what's going on here in just a second. This last display is a typical screenshot showing the OFDM channel power, keeping in mind that OFDM channel power is the power per 6 megahertz. It's not the total power of the OFDM signal, it's the power per 6 megahertz. And each little horizontal blue bar on here represents the RF power, the signal level, in that 6 megahertz chunk of spectrum. Okay, now with that information in place, why do you suppose that in the condition that's shown here for test case 3B with the broadband noise injected before the microreflection, and then with test case 4B with the broadband noise injected after the microreflection, why does one display of MER per subcarrier show the ripple and the other not show the ripple? Anyone want to take a guess? Okay, here's what's going on. In the case of test case 3B, where we don't see the ripple in the RX-MER per subcarrier, the OFDM signal and the injected noise, which in a real cable network could be from amplifiers and so on, are both passing through the microreflection. And when that noise, which now has the same amplitude ripple characteristic as the OFDM signal does, when those reach the OFDM receiver in, say, the cable modem, the adaptive equalizer creates a digital filter with the opposite complex frequency response of the channel response. So that essentially cancels out the ripple in the added noise and the OFDM signal, and the result is an OFDM signal plot with RX-MER per subcarrier showing little or no ripple. Now, of course, you could get ripple in a case like that if the RF input to the modem is low, and then you get the equivalent of additional noise injected after the microreflection, in that case from the noise figure of the cable modem, because you're running a real low carrier to noise ratio at the input to the modem. Now in the case of the lower left display, where we've got amplitude ripples showing up in the plot of RX-MER per subcarrier, what's going on here is the broadband noise is injected after the microreflection. So the OFDM signal passes through the microreflection, gets the ripple in it, but the broadband noise that was injected after the microreflection doesn't have the ripple in it. So both of those enter the OFDM demodulator and the equalizer creates a filter with the opposite complex frequency response of the channel response, which flattens out the OFDM signal, but the noise doesn't have any ripple in it. So there's no, the noise doesn't have any ripple in it. So what we see is RX-MER per subcarrier with ripple. Does that make sense? There's a detailed explanation in the paper of what's going on under the hood there. Now, what made this really strange was that we saw some cable modems would show this stuff coming and going, or some would display it, some wouldn't. So there was some variation that was related to things like total power at the input to the modem, the particular silicon, perhaps the firmware, and other things. So there's a lot of strange things that are going on here, but this is the general explanation of what's happening. Now, here's an example of the edge roll-off, and in this case, the cyclic prefix is set to 192 and the roll-off period 128. And we've got a single carrier QAM channel adjacent to the signal right here on the left, but you'll notice that causes, in this particular example, causes the MER per subcarrier on the first few subcarriers to be impacted because of the fact that the settings for roll-off period and cyclic prefix result in a taper region or guard band that extends down and underneath the QAM signal. And I've got a screenshot, an example that shows that right here. So with these configurations here, this is a spectrum analyzer screenshot. Here's the OFDM signal, there's the QAM signal, and you can see the taper region shape. Well, look where that taper region goes. It goes down underneath the QAM signal. So that means that the presence of that taper region impinging upon this QAM signal is going to impact its MER a little bit. From what I've seen, it's pretty small, generally less than a dB. But in this case, the fact that the OFDM signal is overlapping that taper region means that it's hammering the MER on the first few subcarriers. And that gives us that roll-off. And this is one of those examples where not all modems showed this consistently. We saw this, by the way, in both the field and in the lab. Here's the same OFDM signals, RX-MER per subcarrier, after adjusting the cyclic prefix and the roll-off period to these values. And what's important here is that when you're launching OFDM in your network and you've got QAM signals on either side of the OFDM signal, you really need to optimize, in particular, the roll-off period to accommodate that. There's a table in Appendix 5 of the DOCSIS 3.1 PHY spec. It's in Appendix number 5. And it shows the roll-off period samples in this middle column, and then the right side shows the taper region bandwidth in megahertz. And you can see that for some of those, that taper region bandwidth can be pretty wide, better than 3 megahertz, which means that that taper region is extending away from the edge of the OFDM signal. And if you've got a single carrier QAM signal there, it could be getting into that and interfering with that QAM signal, and likewise the QAM signal could be interfering with the OFDM signal. So make sure you optimize those parameters when you're configuring your CMTS in the presence of adjacent signals. Now there's another thing you could do instead of optimizing that to help improve the overall throughput. You could use bit loading to reduce the bit loading on the first few subcarriers so that they can put up with that lower MER and not have their data throughput impacted. So I think that's a pretty important thing to keep in mind. And so we did some field testing to prove that, yes, this stuff really works in the real world. And in this case, this is using a PNM or proactive network maintenance tool to find RX-MER per subcarrier plots for a bunch of modems in this cable network. And as you look at this, you can see the amplitude ripple in the signal. Now, some people had asked me, well, what are these red lines here? That's the standard deviation limits for the amplitude ripple, and then the black line through here is the average RX-MER per subcarrier. So this was before repairs were done. They found a bad block splice in the network, and they replaced 1 or 2 other components. But this was what they wound up with after they did those repairs. So what it showed was that in addition to using your traditional frequency domain displays, full band capture or spectrum analyzer, screenshot, and signal levels, for OFDM you can use the RX-MER per subcarrier plots as a very, very good troubleshooting tool. So it becomes another tool in the toolbox. Now I want to show you something else that we got from this same system here. Let me see if I can get this guy going. This is a video capture over a period of about 6 weeks or so. Same modem, but watch what happens to the RX-MER per subcarrier over time. Now this tells me there's something going on in that plant, intermittent connections or loose connectors or something. But as you look at that, you can see the ripple coming and going. You can see the edge roll-off popping in and out of there, and all kinds of mayhem happening to the RX-MER per subcarrier. Let this guy continue its journey across here. There we go. This originally started out as something like a 90 meg file, and I asked the co-author who gave it to me, I said, you really got to whittle that down to about 20 meg. So here we go. But what this shows is that RX-MER per subcarrier can vary over time, and does vary over time. Now this is probably a pretty extreme example, but as you look at this, this is definitely an indication that there's something going on in the plant. All right, and that brings me to my final slide. So as most of you know, RxMER has been a pretty important tool that we've used as an industry for the last 20 plus years. Initially on single carrier QAM signals, but it's also a usable tool in the world of Ofdm and DOCSIS 3.1 in the form of RxMER per subcarrier. And rather than have to deal with printing out big long lists of MER per subcarrier values, you can use test equipment that plots this, or you can use third-party applications that plot this. The PNM tool that I showed you plots this as well because it gets that information from the cable modem, and now you have a nice plot of RxMER per subcarrier. This becomes, I think, much more powerful than traditional MER on single-carrier QAM channels because, as I mentioned earlier, if you've got a bad MER number on a regular QAM signal, you know that it's a bad number, but you don't know why it's bad. The number by itself doesn't tell you what's going on. But with DOCSIS 3.1 and RxMER per subcarrier, when you plot that, you can often identify the nature of the impairment. Ingress, what frequency it's on, for example. You can see changes over time, like that video I just showed you. You can see amplitude ripple in some cases. So this becomes a very, very powerful tool in the toolbox to add to your troubleshooting arsenal for dealing with impairments in the outside network. I do encourage you to read through the full paper. It's got a lot of really good information. Even though it's 50 pages, there's not 50 pages to read. The bulk of that is the screenshots from the testing we did in the lab, but there's some really, really useful information in there that I think will help you to optimize the performance of your network and make DOCSIS 3.1 work all the better.
So, yeah, thank you, Ron. It was very informative. I think this type of observability that DOCSIS 3.1 is bringing to our network is just really incredible. It's, the more observability we have, the better we can do with troubleshooting. I guess, Ron, one question I'd have is, I'm blanking now. I had my question all teed up. What's something an operator can do to manage the variation over time of the MER? Because how's my bit loading going to be affected, I guess?
If you're using a PMA app that was discussed earlier, that might be able to dynamically adjust the bit loading to accommodate some of these variations in RxMER per subcarrier. Because it's pretty obvious that in the example I showed in that video, which I think is fairly extreme, but nonetheless it's in an operating cable network. With the MER jumping all over the place like that means that it's going to be difficult or impossible to provide something like 4K QAM. It might work just fine with 256 QAM or 512 QAM, but if you really want to optimize the throughput of the network, I think it's good to monitor these parameters over time and see if they're varying. And if they are varying over time, find out why. It's the usual loose connectors and radial cracks and bad splices, all the things that have haunted us over the years in our cable networks, and those things are going to impact the performance of the Ofdm signal. And if it get as robust as the 3.1 Ofdm signal is with its very, very powerful error correction, it can get bad enough where the higher modulation orders won't work, and you're going to sacrifice the higher data speeds for the customers that are expecting, say, a gigabit class service, and they may only be getting a half a gigabit service.
Okay. Is there any questions in the audience? All right, well, if you think of one later during the conference on RxMER or deploying DOCSIS 3.1, you can track Ron down easily. He's the guy going slow because of the trail of tags from his badge. And then Matt's easy to pick out because he's above everyone else. So thank you for coming out. We appreciate it.